All right, so we're on to 3.2. 3.2 is dealing with logarithmic functions. So after saying logarithmic one time, I'm never going to say logarithmic again. We're always going to just call them log functions. So the log function is the inverse of the exponential functions. What we talked about last time in 3.1, we're talking about the inverse of it this time. So the graph is an exact inverse of what an exponential is. So instead of coming down or going up, we are coming and hugging this y-axis. Before, the x-axis was a asymptote for us. Now the y-axis acts as an asymptote for us. When we're talking about log functions, what happens is if I want to take the log base a of x, this is the same thing as asking, and like if it equals y, this is the same thing as asking or saying that the value of x is obtained by taking our base of a to the y power. So an important note is that every log function can be written as an equivalent exponential function, and this right here can state that exactly. And this would be the process that you would take in order to rewrite that log function as an exponential function. So I'm going to go through a couple different examples. Here's the first one. And I just want to reiterate how we even attempt to find a log function, so it'll help you understand them a little bit better. Log base 2 of 8, it's going to equal 3. And this is because we need to figure out what 2 to what exponent gives me 8. 2 to the third exponent gives me 8, so that's why it equals 3. Again, another example. Log base 2 of 32 equals 5 because 2 to the fifth power gives me 32. Log base 4 of 16 equals 2 because 4 squared equals 16. Okay, so you're sensing this pattern. That the way that we figure these out, in like concerning the fact that these are easy ones to find and all have a nice whole number that we can find in our heads, is based off the fact that we take 4 to what power gives me 16. So you're determining the exponent that's going to give you the number that you need. That's what this log function equals. Some of these we obviously can't do in our head, so we take to our calculators. I want us to find what's the log base 10 of 2.5 in your calculator. So one thing to note, log base 10 is our standard base. So if you ever just see something written as log and nothing else, like log base 5, this is like assumed that this is log base 10 of 5. So your calculator, if you have an older model, is going to automatically associate this with log base 10. If you have a newer model, you can actually input it yourself. So the way that we find this is by going to the math button. You can't quite see that. Going to the math button, arrowing down to A, which is log, and then capital letters base. This will pop you up a screen that shows you log and then enters 2 empty boxes for you to fill in. Your base is going to go down here. Currently that's 10 for us. Up top goes the number that you're taking that log of, which is 2.5. We get an answer of 0.39794. Very clearly, we would have never been able to find this in our head. But what this is stating is that 10 to the 3.97 power gives us 2.5. So some people might say like, oh, I just use this log button. Again, this automatically, oh, sorry, you couldn't see that. This log button right here, sorry, take my other hand away. This log button right here, automatically when you click that gives you a log base of 10. So if I were to do 2.5, I'm going to get the same answer because I used a log base 10. But if I wanted to take the log base 4 of 16, if I did log of 16, that's the wrong answer because I'm log base 10. So I would have to go to math and again down to log base. Oopsie. Again down to log base, put in 4 of 16, enter, I get 2. So little helpful information for your calculator. Logarithmic properties of log functions include the following. So these are all based off of our exponent properties that we learned in Algebra 2. So if we're trying to take log of any base, okay, so A is again going to stand for any number. Any number goes in here, but if 1 is here, it's going to equal 0. This is because they're asking us to what exponent do we have to take A for that number to equal 1. Exponent is always going to be 0 because 0 or anything in the 0 power is going to give us 1. So if we're taking a log base A of A, so basically meaning that our base is the same as where we're taking that log function of, it's going to equal 1. This is for the simple fact that A to any, or any number to the first power gives me the same number. Log of the same base, again, of what we're taking that base to, if it has an exponent attached to it, it's just going to equal that exponent. This is a spin-off of our rule number 3 because it would just be 1 to whatever power that it equaled. An additional rule to this is if we flip-flop this to be a logarithm or an exponential rule, A, the log base same base A of x is just going to be x. Basically, we're saying A to the log base A cancels out here. If you happen to have log of same base on both sides of your equal sign, you get to drop both those logs, and whatever numbers are here remain equal to each other. So I have some simplifying properties for us to try using, or some simplifying functions for us to try using the properties. If I were to be given log base 2 of x equals log base 2 of 3, I want to solve for x. My log base 2's cancel because they're on both sides of the equal sign. Using my property number 4, and x just equals 3. Again, these are going to be super basic properties. More will be added on to these later, but just so you can kind of get the idea. 7 to the log base 7 of 14. Again, same base, same base. Those cancel. I'm left with just 14. Log base 4 of 4. Okay, anytime that we're taking same base of what that log function is taking it of, we cancel these all out, and we're just simplified down to 1 because 4 to the first power gives me 4. Same thing here, same bases, these cancel out. This would technically be 1 times x, so it's just going to be x. Okay, so those are how those properties get applied. Again, we do a little bit more complicated process later, but that's the basic application of them. So another thing to add in, this e always pops back up when we're talking exponential and log functions. So when we talked about this base e for exponential functions, it was when we had e as a base to the exponent of a variable. So if we flip-flop this around then, talking about log functions, this is going to be log base e of x. Whenever we have the specific log base e, we change that out for ln or natural log. Some ways that I've had a teacher that I worked with in the past that called this log natural or log natural, just so you kind of remember that that's opposite. Don't know why. I can't explain that one to you. But when you see that ln, it represents a log base e. This is going to be super important when we're going through properties to understand why these things cancels, because log base e is natural log or ln. So again, these two statements are equal because we're taking log base e of x. Natural log, again, stands for log base e. So it's, again, still log base e of x. If you want to evaluate this in your calculator, I just want to show you where the button's going to be. So let's just take log base e of x or natural log of x when x equals 0.3. I just want to show you where to find this button at. If you come down straight below the log button and go to ln, hit that and point 0.3, we get negative 1.203. So that's just as easy as that one seems. So since we had properties for log functions, we also are going to have properties for these natural log functions. They are just spin-off properties using ln in place of log base a, just to show you that these same things roll over when we're talking about natural log. So if we were to take the natural log of 1, it equals 0 again, because this is log base e of 1. E to the 0 power is going to give me 1. Same thing as before. This is technically log base e of e. That's going to equal 1 because we're taking same base as we're taking that function up. So e to the first equals just e. Again, same property, log base e of e to the x is going to equal x, just as e to the natural log of x is going to equal x. And same sides of the e, or different sides of the equal sign, same log, drop them, we just get x equals y. So we're going to apply these properties super quick. If I'm taking e to the natural log of 5, I just want to really reiterate that since natural log, or ln, equals log base e, these cancel because they're the same, and we're just left with 5. Here in this scenario, natural log of 1, anything log of 1 is going to be 0. Since we have this 4 out in front, though, the 4 carries over. Times 0, it's just going to equal 0 in the end. Natural log of 1 over e. So I'm kind of getting a little bit more complicated ones here. Nothing crazy, but exponent properties say if we have something in our denominator and we want to bring it up to our numerator, you just have to throw a negative exponent on it. The exponent down here was technically 1 when it's not there, so I make it a negative 1. So this reiterating would be log base e of e to the negative first. Since these cancel, it's just going to equal negative 1. All right. So that's all we have for talking about log and log properties. There's going to be a little bit of a worksheet over this. I haven't decided if it's going to be a worksheet or problems out of the book, but just keep posted for whatever assignment I throw in here for you. Okay? Thank you very much.